Now the determinant is defined for any n by n matrix. Unlike what the title is saying, determinants for 2 by 2 and 3 by 3 matrices, right? The determinant takes in a square matrix and returns a number in R, right? So you can view the determinant as a function that maps R n by n towards R, okay? Now, you have probably dealt with determinants before, possibly while using, I don't know, the Cramer's rule, for example. You should know in vector calculus, the Jacobian matrix, if you've ever heard of the Jacobian matrix, which is the matrix of first order partial derivatives of a multivariate function, well, it turns out that the determinant of the Jacobian matrix, simply called the Jacobian, is a key factor in performing change of bases for higher dimensional or multivariate functions. Although the determinant has theoretical uses, because of the complexity of its calculation, we'll see that computing the determinant is not a piece of cake. It requires many calculations. A determinant is seldom used in practice unless the matrix size is small. In this and the further coming lectures, we will begin with the definition of the determinant and then discuss its evaluation using expansion of minors and Gaussian elimination. We will also be giving some applications of the determinant in further lectures. So that said, if you've got a scalar, let's say the matrix A is just a scalar 1, then the determinant is only that scalar, right? Now let's go to the 2 by 2 case. So I've got A11, A12, A21, and A22. Now first, what we do is list the products without any sign involvement. You should know that the determinant of an n by n matrix is the sum of all possible products of n elements formed by choosing one element from each row. So you focus on one row out of your own choice. You choose a row. Let's say I'm going to choose the first row, okay? And you start moving element by forming all products with respect to this element. So let's pick A11 and form the product of A11 with all its possible elements. What are they? So you have to eliminate the first column, the row and column that A11 belongs to. So A11 multiplied by what remains, that is A22. Then you go on to the second element, that is A12. So A12 multiplied by what? You eliminate its corresponding column and row, and you're left with A21. Next, to determine the sign, if each product is negative or positive, you could always start by a plus and then you flip. So plus, minus, and so on. So this guy is a plus, since A11 is facing a plus, and A12 is facing a minus. Hence, the determinant of this matrix is A11, A22 minus A12, A21. Now, of course, we could have picked the second row and done the same thing. You would have reached the same expression, right? That's why you find most people that compute 2 by 2 determinants, they do the following. They do the cross thing. It's this guy times this guy minus this guy times this guy. So this is another way of keeping it in mind. Now, if we were to compute a 3 by 3 determinant, we can pick a row and do the same thing. So first, let's lay the signs, plus, minus, plus. Focus on the first row and start with A11. So A11 multiplied by what? We've got a plus A11 multiplied by something, right? So we have to eliminate its corresponding column and row, and we're left with this submatrix. So it will be multiplied actually by the determinant of what is left. That is A22, A23, A32, and A33. We move along A12, eliminate its corresponding column and row. We're left with A21, A31, A23, and A33. That means we've got a minus A12 multiplied by the determinant of what is left. And last but not least, we're left with A13, eliminate its corresponding column and row, and there's a plus. So plus A13 multiplied by the determinant of what is left. That is A21, A22, A31, and A32. Right? So now let's compute the determinants of smaller 2 by 2 matrices. Using what we had previously, we can do, this guy becomes A22, A33 minus A23 and A32. This guy is A21, A33 minus A31, A23. And this guy is A21, A32 minus A31, A22, right? Replacing, we will get A11 multiplied by A22, A33 minus A23, A32 minus A12 multiplied by A21, A33 minus A31, A23, and last but not least, plus A13 multiplied by A21, A32 minus A31 multiplied by A22, right? So this is the determinant of a 3 by 3 matrix. As you can see, if you would count the number of products, so for a 2 by 2 matrix, we get 2 products formed by, this is the first one and this is the second one. In a 3 by 3 matrix, you'll get, here you've got 2, so A11, A22, A33, and A11, A23, A32, and 4 more, so 6 products. In general, for an n by n matrix, if A is n by n, then the determinant of A is formed through n factorial products. Not easy. Now, to see that this is a really large number, go ahead and compute the number of products, not the complete determinant, the number of products of a 15 by 15 size matrix, a moderate size, So an example, if A is just 15 by 15, then the determinant of A would require 15 factorial products, which is 1,307,674,368,000 products. That's a lot. Okay? So the thing to keep in mind is that the determinant requires a massive amount of product computation. As you can see right here, this is an unbelievably huge number of products, and it will be futile to try to use the definition of the determinant even with a computer with massive capabilities. Okay? Notation: in some references, you will find that the determinant of A is referred to as det of A, and in some others, you will find that you will see an absolute value around A, which also refers to the determinant. Now, in the next lecture, we will introduce the concept of evaluating a determinant using the so-called expansion of minors. As you can see, as we did over here, right here, we saw that we represented the determinant of a 3 by 3 matrix using smaller determinants, that is, determinants of 2 by 2 matrices, right? Now this process is really similar to the expansion by minors, which we will see in the next lecture. Okay? So in this one, we talked about determinants of simple 2 by 2 and 3 by 3 matrices, right? Gave an example on that. And we also computed the number of products required for determining the determinant of a matrix, which is n factorial, an extremely large number even for moderate sized square matrices.